Okay, so we start the second lecture by Alexander Petrovich Veselov from Loughborough University. He will speak about differential algebra of polytopes and inversion formulas.
Okay, many thanks for this opportunity, and sorry for not being in person. I'm trying to think when I first met Sabir. You know, I was student of Sergei Petrovich Novikov, but I did attend Arnold seminars, especially in September, and you know, when Vladimir Igorevich generously shared his thought about open problem. And I attended actually all special courses of Arnold, who was, from my point of view, the best, the most influential lecturer. And so, but I think as a mathematician, I saw Sabir talking about these monodromy groups of this paper, which was published in 77, but it's submitted in 75, and it's I think it was in 1975 probably, and that I think it was a talk of Sabir at Moscow Mathematical Society, which was actually kind of itself a big honor. But they talk. I remember that the lecture was very. I was very impressed by the lecture, and actually when I preparing the talk, I start reading this. It's beautifully written, also paper with a lot of pictures and very clearly. And the very first sentence, the theory, the Picard-Lefschetz theory, is a complex analog of Morse theory, which is a kind of you know. To me, that was a kind of, you know, eyes opening to this thing. So when I have chosen the talk, the choice of my talk, this will be based on our recent work with Viktor Matveevich Buchstaber, and we did several joint works, in particular related to cobordism theory. And as you know, Sabir made a very substantial contribution to algebraic topology and cobordism theory. But eventually I have chosen the topic which was actually it was Sergei Landau who determined this, who gave me this present, right? I mean, in our meeting in May. So I thought that it should be called maybe the talk of the tale of two polytopes, but it's not quite two polytopes, it's two series of polytopes, but it is indeed essentially a kind of extra maybe piece in the story of these polytopes, you know, the famous polytopes, which I was personally very much puzzled, and I will explain actually the sentence. Now, this is a joint work with Viktor Matveevich Buchstaber, and most of the stuff I learned from him, and I will explain what of it. So this is about. So let me just start. So the beginning is a very classical problem. You have power series, and we assume that the first coefficient is 1 for simplicity, and we consider inversion problem for this power series. And it goes back to Lagrange, and Lagrange gave some way to answer this question, but this is completely different. This is kind of combinatorial, no algebraic. So we can see the coefficient of the inversion are actually polynomials of coefficient of the series, of power series. And these polynomials have, for example, G1 is minus F1, G2 minus F2 plus 2F1, and G3 is this, and G4 is this, and so on. I mean, forget about sign. Sign is actually it's actually very easy to explain. So let's look at the coefficient, this 155. And but before that, I want to say that this is of course well known that inversion of a simple power series like arctan, for example, has a very simple, but inversion tan has highly non-trivial, although rational coefficients, right? Now, I think it was Loday in 2005. I tried to trace who was the first to notice the relation of these numbers with combinatorics of Stasheff polytopes or associahedra. So let me so associahedra are relatively young object, and it's a bit surprising. Well, I mean, I don't know. It's that it's not very natural object maybe, but very important. So it appeared in Stasheff in algebraic topology, by the way, related to H spaces, and this is kind of if you have associativity ABC equal to ABC, you can view this not as equality but up to homotopy, and this is what H spaces. You have generalization of the group when you replace equality by homotopy. So left-hand side is not equal to right-hand side, but is homotopic too. So you can view this as homotopy. So this will be kind of interval. Will denote this, and this is the first associahedron. It's A2 actually in my notation. Stasheff polytopes is usually defined as K. It will be K3 in Stasheff notation, but let me use A for associahedron kind of. Now you can define it as Newton polytope of certain polynomial, and its combinatoric is indeed very rich, and the number of vertices, for example, Catalan numbers, are not like all these numbers, but Stanley had more than 200 interpretation, combinatorial interpretation. Catalan numbers, one of them is this is a number of vertices. And what's important about associahedra is that all faces are products of associahedra of smaller dimension. And so in particular, if you look at this three-dimensional associahedron or at this t-shirt, so then you see that it's either I should say that pentagon is two-dimensional associahedron, and the three-dimensional associahedron has faces either pentagonal, which is associahedron of smaller dimension, or product of, which is this product of segment of interval, which is quadrilateral. And we have 3 quadrilateral, 6 pentagonal, 21 edges, and 14 edges. And this is remarkably, if we look at this formula for G4, then you see this one responsible for associahedron, and 6 is pentagons, 3 is F2 square. F2 is exact, and it's also explained why we have chosen this index, why our associahedron has index a bit one higher, in agreement with this. There are probably deeper version, deeper reason for this kind of shift of, but anyway. So this is exactly 1-to-1. 14 in particular, 14 is Catalan number, and this is just number of vertices of it. So the story is actually, as we know, I mean, Stasheff, strictly speaking, defined this as a combinatorial only object. Milner, I think, was the first to ask the question of realization, and it's so usually it's the proof is that it can be realized as a convex polytope is usually ascribed to Milner, although it was not published. And actually, I asked Milner how he proved it, and he said, I forgot. And but he said that I remember that I did even 3D version of this Stasheff polytope. Anyway, the first proof is so it's non-trivial. The fact that some combinatorial polyhedron can be realized as convex polytope is not quite trivial, but now we have many construction of this. Probably it's Hyman and Lee should be ascribed. So it means that this object is quite quite rich and geometrically non-trivial, not natural, maybe geometrically, right? Now there is another problem, namely we can ask for multiplicative inverse of series starting with 1, and then we have similar polynomial here. And again, this is famous that if you have, for example, this series, the AX, that inverse is generating function x divided by x minus 1 is generating function of Bernoulli numbers, which are probably the most important rational numbers, and they appear everywhere. And in particular, term x is also expressed in terms of Bernoulli numbers, but with to some coefficient. So, and in this case, it's not, it's at least, anyway, I learned it from Aguiar and Ardila paper 2017, who said that this is actually a similar observation to Loday, but in that case, associahedra should be replaced by permutohedra. And actually, this is where I was hooked by from the paper of Aguiar and Ardila. I thought that I would like to understand it better and maybe prove this in a simpler way. And actually, the purpose of the talk is to explain this and to give kind of elementary proof using elementary integrable PDEs, right? I mean, this is how you can view this. But there are some interesting connection which I'd like to talk to. So what is permutohedron? Permutohedron is much more natural, and it goes back to probably Schur. And so it's you just take a vector 1 to n and consider orbit of action of symmetric group and take convex hull of this orbit, and that would be, and this is the same as Newton polytope of van der Monde polynomial. And it's historically, indeed, it was image of moment map. You consider Hermitian matrices with given spectrum, lambda 1, lambda n, which must be real. And let's assume that spectrum is simple, and you look only at the diagonal elements, which are known to be real. So you have a map from this space of isospectral from matrices with given spectrum to the diagonal, and this is moment map. And the image is actually exactly permutohedron, and sometimes it's called Schur-Horn theorem, and it's Isaiah Schur goes back to at least to him. And in that case, it's kind of natural. You have n factorial vertices, a lot of facets actually. This is. And what's remarkable about this, that this is again, all the faces are, and the first one in associahedron start with pentagon, right? The series, and this is with hexagon, and then you go extend it to any dimension, and this will be permutohedron, and combinatorics is independent on lambdas. And in particular, we have 8 hexagonal. It's actually in dimension 3. You take octahedron and truncate it, octahedron. So in that case, it's kind of natural, you may say, truncating, it's cutting all the faces, all the vertices, right? I mean, that's quadrilateral corresponding to vertices, and from triagonal you have hexagonal. So this is numbers, and they exactly fit very well with inversion of. Okay. So let me explain what I again learned, very important, very useful construction, which I think, I mean, graph associahedra is, I think it's not, it's used in different, I think, maybe version. In particular, I think Fomin and Zelevinsky had their own construction. So this, I think, goes back to Carr and Divadas. So this is, so if you take any simple connected simple graph, simple, and no double, no loops, and with the set of vertices, and consider, it's called building set sometimes, B of gamma is the set of all connected induced subgraphs. Connected induced subgraph means a subset of, we will identify, yes, subsets of 1 to n, such that restriction of gamma on this set is connected, right? And this is an example. And then graph associahedron you can define as truncated simplex. And so, or you can give it explicitly by restriction. There is one relation, which is 3 to the n is not very important. It should be subadditive, superadditive. But just for simplicity, this is kind of explicit if you want convex polytope, which is defined by the graph, right? I mean, and combinatorics. So combinatorially, it's the following. So in this case, graph is, this is, by the way, a picture from Carr and Divadas, and everything I learned from, I mean, it's very nicely explained. So you can see the, so your graph, yes, you have a graph, which in this case is this, what is shown here. And vertices of the graph are faces of simplex, faces of simplex. And then you start with subgraphs of largest subgraph, for example, here. And here, for example, I have subgraph with 3 vertices, right, on the second one, right? So these 3 vertices corresponds to 3 faces. 3 faces determine a vertex in this case, and you determine you a vertex and you truncate this vertex, right? And there are 3 such subgraphs, so you truncate 3 vertices here, right? Then you take the next one, it's subgraph of length 2, they correspond to edges, then you truncate edges, and that's it, and that's what you get, right? So it has graphosahedron has a very clear combinatorial description or geometric description, if you want, as truncated simplex. And if you need explicit equation, then they are here, right? And why it is I mentioned this, because there are associahedra and permutohedra corresponds to path and complete graphs, the simplest possible graphs in a way, right? Opposite, by the way. I mean, complete graphs is when all vertices can, and this is path, right? Simply an kind of linking diagram, and associahedra. Okay, so now let me. In that sense, from the point of view of current dividers, graphosahedra, they are natural choice, at least, right? I mean, there is no mystery, but right. So now let me explain now what I learned from Victor Matveyevich Buchstaber, who start thinking about this, I think, more than 20 years ago, and so this is the problem. I mean, let's it's again terminology. I would like to call it Grothendieck rings of combinatorial polytopes, but Grothendieck rings it's already used in different. It's used by McMullen, and the sum is Minkowski sum, for example. So this might be confusing. So let's call it P. So what is it? It's a very natural thing. It's like Grothendieck did free abelian group generated by all convex polytopes, but they considered up to combinatorial equivalence. So for example, McMullen, he considered convex polytopes as a convex polytopes, and then Minkowski sum you define, and anyway, here it's convex polytopes considered up to combinatorial equivalence, and the product is defined by the product. Okay, so what is what I remember when I first heard Victor Matveyevich talking about this, and I was very much puzzled by his definition of derivation, better say. It's just sum of all facets. Facets are faces of codimension 1. Right, and you consider this as an element of our Grothendieck ring, right? So this derivation is simply taking boundary but splitting them, considering them. It's boundary of cube, for example, will be 6 quadrilateral, simply, without any signs. And that's the fact that orientation was ignored, and that d square is not 0. I mean, I was kind of puzzled by such a thing. But then Victor Matveyevich showed some results which shows that it's actually quite interesting, and actually it eventually explained this theorem which I by Loday and about inversion, right? Anyway, so for the boundary of graphosahedra, we have a nice formula, and namely it's a product of PDEs is so S is element of this building set on gamma, so it's graph associahedron of related to this connected subgraph, and P gamma S is a kind of you just contract S on gamma, and this is gamma quotient S. And formal definition is that graph gamma S has a vertex set n minus S and has H between two vertices whenever they pass connected in the restriction of. So, okay, so now, let's consider now, right. So in this definition, we took only boundary, right, facets, right? We don't have, let's now count in all the faces, but with coefficient t to the k, weighted kind of set of this. So fp of t is sum of t to the k times sum of all faces of codimension f, right? So now this polynomial in k in t counting all the, and these faces considered as elements of our Grothendieck ring, of our ring of polytopes, right? And for simple polytopes, fp of t is actually exponential. This will be important, and I think this is observation. So this is important observation for, it was very important for Buchstaber in what follows, right? So for simple polytopes, but otherwise it will not work. So this fp of t is a solution of, so you start with p, and then you consider, you recover the whole combinatoric by solving the equation d by dtf equal to df, where d is Buchstaber derivation, right? D square is not zero. And so this is the thing, and then we defined Motivic interior as of polytope as fp of -1. So it's so basically I think this is this -1. You know, people in it's essentially, it's very much parallel to what Asik Khovansky and Sasha Pukhlikov did in this, and in fact it's in a way maybe even can be like interpretation of their result, but conceptually this is kind of interesting because you want to consider so strictly speaking open so let's take open cube, right? We want to undressed cube, right? We take first all the facets, right? And so subtract this facet. But it's not good because we subtracted edges twice, which is not good. We have to add edges. But then you have a problem with this, right? And so this is a kind of thing. So eventually, so what you have here is, of course, why it's Motivic interior? Because strictly speaking, it's not a polytope, right? Because it's open, it's undressed polytope. But we consider this as element of this Grothendieck ring, right? It is, so it's kind of Motivic in interior. And for it's funny because if you consider t as time, at t equal to 0, you have dressed polytope, proper cube, go to time -1 before, and then you see kind of naked cube, right? Which is, and the time is exactly -1, and of course, people familiar with the theory of polytopes knows that this shift t to t -1 is kind of anyway. So it's just going from t to t to 0 to t minus 1 is undressing. That's the thing, right? And now what's coming back to associahedra and permutohedra. So let's consider A will be generating function of all this facet function of a f a n t. We multiply by x to the n plus 1, and this is generating function of this phase polynomials of associahedron. Remember that fa of t is sum of all faces of associahedron taken with weight t to the n, right? And then the same for permutohedron. And that was a Buchstaber result, which convinced me that it's actually probably quite a clever way to do, because what is so this generation function satisfies certain PDEs. In fact, second is of course not quite PDE, but anyway. So the first one is famous Hopf equation, and how to prove it? It's easy. It follows from the boundary formula. You know, for graph associahedra, you have, look at this, for example, DAN. You have to take connected subgraph of length I, and you will have something like I plus 1 of them. And after you shrink this, you have an minus 1, and this is a formula for, and this is equivalent to this, right? I mean, it's not the main thing here. I think it's not the calculation; it's kind of conceptual. It's point of view on this, right? So then it's so you have this, and it's quite non-trivial, because here, look at this. You consider usual generating function, and for permutohedron we consider exponential generating function. And this, you know, it's still puzzling me. Sometimes you consider exponential, sometimes generating function. Why it should be? I mean, I think there is something here I'd like to understand better. But Hopf equation, right? I'm just so this is sometimes called in Wiskid Burger's equation or Riemann equation. I mean, it's very, very simple. It's the first nonlinear equation, and you can solve it very easy. This is a solution, u equal to f of x plus ut. It's implicit solution, right? So from here you have to express u, right? So if you have initial value, you have, and because you have to express, and this is implicit, you have this breaking waves, you know, the famous how overthrowing waves, right? I mean, this is phenomena, and this is, but how it is. So in our case, remember that initial data is a of x, right? I mean, let me. A of x is, what is A of x? Initial data for Burgers. For this, it's just generating function of all associahedron, right? So you take Burgers equation, in Wiskid, and then you have this. So I'm just using this formula from PDEs, from elementary PDEs, and applying it here, and then I have a solution which satisfies this, right? And if I substitute now, remember that t equal to -1 is taking interior, right? So I substitute here now t -1, right? So I want to undress this now, and then I have this relation, and minus appear here, and if I write it down, xi this, then x equal to xi plus, and this is, so you see that xi, it's one series is inversion of another. It's really better to do it, you know, on the paper to see, but it's really elementary. If it's just using solution of Hopf equation, right? And from here it follows that if you consider generating function of associahedra and generating function of interior of them, then they are compositionally inverse. Now, this is exactly what Loday say, because remember that this formula is just the formula of for which I have started with, right? So the same about permutohedra. It's even simpler because in this case it's ODE essentially, but X dependent. So you have explicit solution like this: P divided by 1 minus T. Again, we put T equal to -1 to have, and then we have this, and then we have this relation. So 1 minus undressed permutohedron is 1 over generating function of rest. And this is, so it means that undressing is equivalent to taking inverse, and this is multiplicative inverse. Okay, so, and it looks a bit maybe mysterious, but let's look at this, and this is related actually to Professor Luengo and work by Sabir with co-authors about 20 years ago about this power system. And anyway, but it's in a different way. So we can consider Grothendieck-Ring if photonic varieties. It's quite natural. You can define. So you have Grothendieck rings which were defined yesterday of complex quasi-projective varieties with relation x equal to y plus x minus y. So you have completion also. You have also complements to closed submanifold as elements of the ring, and then we can define Matveev interior exactly in the same way. For toric variety, we can define Matveev interior by this by this formula, and its Matveev interior in this case it's just algebraic torus. It has to be shown, and it is essentially the same argument as in the previous case. And as a result, we have and permutohedral variety, of course, it's a toric variety corresponding to permutohedron. And then from the same argument, we have that generating function of permutohedral variety in the Grothendieck-Ring and generating function of algebraic torus, which is undressed permutohedral varieties is torus. They inverse to each other. And now this actually links with this explains one of the formula about permutohedral variety is what is Poincaré polynomial. Poincaré polynomial turned out to be Eulerian polynomial, and this is indeed this is actually Euler's indeed calculation. So you see p plus 1, p squared plus 4p plus 1, p cubed plus 11p squared plus 11p plus 1, and this is actually how he came to this. But now we have also these coefficients are Eulerian numbers. They have interpretation. A and k is number of permutation in a Sn with k ascent. It's a lot of combinatorics in this. So this is coefficients are Eulerian numbers, and what we have as a corollary that Poincare polynomial of permutohedral variety is actually Eulerian polynomial of T square. Right, and this fact was known, I don't know, since 1990s, so it's not new, although it's difficult to trace who was the. But in our case, the proof is very easy. So we consider the right-hand side is, so we have to consider motivic Poincare polynomials for algebraic torus. So you have C star. C star is CP1 without 2 points. CP1 has T square plus 1, right? And by motivic, we have algebraic C star has T square minus plus 1 minus 2, so T square minus 1. T square minus 1 is motivic Poincare polynomial of, and for the torus, it's 2 to the n. And if you just write elementary, and then you just compare with Euler formula, and it's genuine Euler formula, right? So it's kind of calculational proof, which is quite nice. Now associahedra. That's very interesting because, okay, so for toric varieties, it's clear that you have what is interior. Interior is probably algebraic torus, probably, right? But what's about Deligne-Mumford? And Deligne-Mumford space is special compactification of M0n, right? Which is so we can, in that case, again, we can say we know what is interior. Interior is M0n. It's n ordered point on CP1, distinct, considered up to projective equivalence. So it's kind of thing, and then we have similar situation to the toric situation, right? It's not toric, and actually there is, I should mention, there is Lossif-Manning compactification of M0n, which is permutohedral variety, right? So you may say that permutohedral variety interior is M0n if you Lossif-Manning, right? I mean, it's not quite clear what is interior. That's what I mean. It's not very well defined. But for Deligne-Mumford, of course, everybody would agree M0n is undressed Mn. I mean, because this is the way how M0n bar appeared. Now, Getzler, remarkable result. Exponential function of Poincare polynomials of open and closed Deligne-Mumford modular space are inverse to each other. And McMullen showed that similar thing is quite works also over R. So we looked at, of course, as Sasha Warchenko did in the first lecture, over finite field. What happened over finite field? Over finite field, topology disappear. You can count only number of points, right? And this is number of points. So and then the theorem is that it will be true over finite field FP if you consider simply this number of points over on it. But this is again is based on results of Euro-Shabbat with co-authors of 2017. I mean, we basically who computed this numbers in Deligne-Mumford spaces as okay. So right. So let me now discuss why only associahedra and permutohedra. Okay, well, from graph-associahedra point of view, it's clear, simplest, complete graph and path, right? I mean, it's a thing. And but let's look now from our point of view. So what we need, we want to have subring cloned under differentiation, under derivation, right? Taking the boundary facets, right? I mean, it's so. If we consider, if we restrict ourselves by graph associahedra, then we can prove that it's only associahedra and permutohedra has. So basically, if you want, we start with pentagon, and then the next one, you might think that you can take the dodecahedron, right? Because the boundary is pentagons, right? So it's good, but actually it's wrong, because you cannot continue. Actually, you can continue probably in dimension 4, but in dimension 5 it won't work. You have to choose associahedron, right? But we cannot prove it, right? So this is we can prove it only if you stay in graph associahedra, but this is very small subspace. I think this is one of the most interesting question is, so what are other sequences of with this property? So if you take sequence of polytopes in every dimension 1, indecomposable. Decomposable is, I mean, you take cubes, for example, I mean, but they're decomposable. In decomposable, it's presumably only simplices, associahedra and permutohedra. And simplices, actually, from this differential equation point of view, they are quite elementary. They satisfy this, but they're also interesting, but somehow aside. It's a universal appel sequence. And universality, these universal coefficients are actually simplices themselves. And Bernoulli and Hermite polynomials, they part of this appel sequence. It's an interesting story, but aside, it's not one. Just to say that if you modify question a little bit, then you can find more interesting. And of course, we looked at the cyclohedra, and this is Buchstaber also actually looked at this, and then we looked what it's a kind of moduli. The boundary is made of cyclohedra and associahedra, so it's a kind of module of associahedra, right? So you have associahedron equation and then linear in VC. And you can solve it easily, and as a result, you have combinatorial interpretation of Faraday-Bruno formula. Just to say that there are possibilities, but this is not. You see, it's not closed. It's not. It's module of associahedra. We start with associahedron, right? And just to finish, really. Let me, so I came, of course, you know, from integrable system point of view, and one of the magical development is this Witten Kontsevich result that Kontsevich-de Vries equation hierarchy describe generating function intersection number on Deligne-Mumford spaces satisfy Kontsevich-de Vries hierarchy. Now, when G equal to 0, then you reduce to this, and that's kind of, you have elementary. In this case, intersection numbers are multinomial, and this is kind of related to the story. So one might think, so so therefore you can view this as dispersionless limit of hierarchy, and of course elementary kind of limit story when but the full story is and that's raised the question what so we basically solving Hopf equation, and we give interpretation as certain elements of ingrothentic ring of polytopes, right? And I think the first person who thought of using integrable hierarchies elementary in combinatorics, elementary of this style, was Alexei Boris Shabat and Seva Adler. And Alexei Boris has this paper about the relation with Fourier de Bruno, and Seva Adler, I think, raised it to the more general situation, but it's still mysterious. I mean, the possibility of using elementary integrable system in combinatorics, and it's still it's kind of I think has to be understood, and this is just the beginning. So let me finish. Many happy returns, Sabir. Great to see you in good health, and let's. That's it.
Thank you very much. Let us thank the speaker. Are there any questions?
You define the motivic interior by plugging -1 to some polynomial. Did you compare this with the Ehrhart reciprocity? There is famous Ehrhart reciprocity.
Yeah.
Maybe I pronounce it wrong.
No, it's yeah. I mean, I like Ehrhart story a lot, and it's certainly remind us it's related story, right? I mean, there is Ehrhart, of course, which counting integers inside of scaled polytopes, and you have Denson-Merville, where this f vectors, how many faces of different dimension convex polytope may have, and then you have this Denson-Merville relation, which is, so if you consider generating polynomial of f numbers, and let's call it p, then p of t minus 1 is what is it called?
H polynomial it's called.
Sorry, palindromic. Yes.
H polynomial it is called.
Yeah, it's palindromic. So you have to shift by t minus 1, and actually the best explanation and the beautiful explanation, there is a paper by Asik Khovansky who explaining this from kind of more theoretic point of view, but I think relation with toric geometry was instrumental in solving this problem, how to describe all relation on f number. So it's Denson-Merville is definitely this t minus 1, right? I mean, for me, this is shift by 1, which is on one hand is we have seen it many times, but I think it's deep. So there is something deep here, and it's the same phenomena, shift by 1 time.
Okay, thank you.
Right. I mean, Euler characteristic, if you want, its value at -1. -1 is old, of course, number.
Okay, thank you.
Sasha, that's Serежа Lando.
Привет, Сережа.
I think that your question about when one takes ordinary generating function or exponential generating function can be answered in terms of Hopf algebra structure. In fact, your differential, you consider is more or less the co-multiplication in the space of polytopes. And it can be found in Aguirre-Ardila memoir.
Correct.
And
I should have mentioned this, right? I mean, it's they using their paper called Hopf algebras, and this they have a proof of explaining this exactly the way you say. So it can be understood in terms of Hopf algebras, and this is done by Aguirre. And so from my point of view, what we did is a kind of maybe more geometric, maybe more elementary, because we're using this. But you're right. This is exactly Aguirre-Ardila, right? I should have maybe mentioned this link with Hopf algebras.
yeah,
Very relevant. Very relevant.
I don't know whether you have paid attention to my paper with Chmutov and Kazaryan about relationship between combinatorial invariants of graphs and integrable hierarchies. And
maybe I missed this, Sergio.
And also how Hopf algebras are involved in this picture. Maybe.
Send me, please, thing. But while it's you know, if you consider, for example, Deligne-Mumford, then let me show something which I don't understand quite. Look at Getzler, right?
Yeah.
Inverse to each other compositionally, right?
Yeah, it's true.
But you have n factorial. It's different from what we have. Now, but McMullen, for real version, you don't have n factorial. So this I mean, I know that, of course, you know, this is kind of the real M0 n bar is glued from n factorial associahedron, right? So it's naively, you have to divide, right? If you go to, but anyway, it's kind of, it is true, but here you have, and in our case here, you see, we also have to divide by n factorial over p, right? So strictly speaking, so what I was talking about, right? There was no n factorial. Now it's I frankly must say that I don't quite understand this swap from. There is probably some deep explanation, but if you remember the beginning, my series, there was no n factorial. It was genuine power series, right? And all these things was genuine. But
but
McMullen already have no n factorial, right?
Yeah, that's because n factorial always arises if it's the order of the automorphism group. And if your automorphism group, if you have a real picture, it will not be n factorial simply because the automorphism, there is no automorphism permuting mark points. But I myself do not understand the real Deligne-Mumford model.
Yeah, it's quite tricky. Even fundamental group, I think, cohomology ring is subject of big paper in Annals, I think, of real version. It's quite complicated object.
It's rather complicated, yeah. Okay, thanks.
Okay, if there are no further questions, let us thank the speaker again.
Thanks.
We have a lunch break.